Hello everyone, welcome to this lesson. So in this lesson, we're going to continue our discussion on numerical integration. Now, what we learned up to this point, we learned two techniques. We learned the trapezoidal technique and we learned the Simpson's 1/3 technique. And the trapezoidal technique uses a first order polynomial, right? And the Simpson's 1/3 uses a second order polynomial. And when we're dealing with a trapezoid and maybe our approximation is not good, what we can do is either we use more trapezoids or we use a higher order polynomial and go with a Simpson's 1/3. And say, for instance, we use a one application Simpson and that is not accurate. Well, we can use multiple application Simpsons. Now, there's another technique that is actually superior to the Simpsons 1/3 in terms of finding better approximations. And this technique is dependent entirely on the trapezoidal rule. And the technique looks like this. If I have one approximation of a trapezoid, for instance, if I approximated this function, which is e to the x, from 0 to 1 using one trapezoid, and I have this approximation, and I created another approximation, instead of using one trapezoid, I use two trapezoids. So I can take this approximation with one trapezoid and approximation with two trapezoids, and I can combine them in a unique way, which I will explain in a bit, to get an even better approximation. So this technique is called Romberg integration, basically taking a trapezoidal approximation and a more accurate trapezoidal approximation and combining it to a more accurate approximation. So I can take this one step further. Instead of taking one trapezoid and combining it with two trapezoids, I can take two trapezoids and combine it with an approximation using four trapezoids, and I can combine those and get an even better approximation. And I can do one step further. I can use an approximation using four trapezoids and an approximation using eight trapezoids, and I can combine them and get an even better approximation. I can go even a step even further, use an approximation using 16 trapezoids, combine it with an approximation using eight trapezoids, and get an even better approximation. Now, if you noticed, the approximation that I mentioned, where when I used one trapezoid, two trapezoid, 4, 8, and 16, and you can find that the difference between the ones that I combined was one was the half of the step size of the other. In other words, using two trapezoids, the widths of the trapezoids are half of that when you're using one, and where I'm using 8 trapezoid, that's half. The segment has half the width of when you're using 4 trapezoids, and so on. So you have to use this type of criteria when you're combining two estimates. One has to have half of the step size, or in other words, half of the width of the segment, than the other one. Okay? So let's go ahead and actually see how those are combined. And let's actually use the first two approximations. The one using one trapezoid and the one using two trapezoids. And this is the equation of how you combine these two. Okay, so I'm going to take the more accurate one, and I'm going to give it a weight of 4/3, and I'm going to take the less accurate one, and I'm going to give it a weight of -1/3. Okay, and you can see these add up to 1. And this is how I'm going to add both of these. I'm going to take both, I'm going to give them different weights, and I'm going to combine them into a better estimate. Okay, I'm not going to go through the derivation of this. The derivation is available in a lot of the numerical methods textbooks. Now, what we can do here is we can actually create a general formula for different combinations that we have, because this one is more restricted for combining when you're dealing with one trapezoid and two trapezoids. What if I want to combine two trapezoids and 4? What if I want to combine 4 with 8 or 8 with 16? Well, this is where this general equation comes into play. Okay, so J here indicates the less accurate and the more accurate integral. In other words, j equal 2 is more accurate than j equal 1. K is the level of integration. Okay, when we created those estimates initially, that's the first level of integration. When we combined both into a better estimate, that is referred to as the second level of integration, which means in this case, K is 2. Okay, so let's actually see if I use K as 2 and I use J is equal to 1. let's actually see if this reduces to that. So if k is 2, 4, 2 minus 1, that's 4. And here, that's also 4 minus 1, that's 3. So 4 divided by 3, so I have this. And also have negative 1 divided by 3. Okay. And you can see that when j is 1, that's 2 and 1, and this is 1 and 1. And we said j is basically indicating distinguishing the difference between the more accurate integral from the less accurate integral. And you can see that's I21, which refers to when we're using 2 trapezoids. And this is I11, where I'm using 1 trapezoid. And these combine into I12. And k, when k is 2, it says that we are at a second level of integral. Now, to explain this further, I want to go, so you can see this is actually a notation of a matrix, right? So where j is the moving through rows and k is moving through the columns, right? So if I look at this, I11, that is my first estimate of using 1 trapezoid. And this is I21, which is using 2 trapezoid. And we actually use this Romberg integration formula to combine these two into a better estimate, which is I12, right? So this is called a one application Romberg integration. You can see this is basically a 2 by 2 matrix. So we only have those 3. So what about this what if this approximation is not accurate enough? Well, what I can do is I can go ahead and get a approximation of the trapezoid that, say for instance, if I got one with 1 trapezoid, then I got with 2 trapezoid, I can go ahead and get one with 4 trapezoids. And then I can take the one with 4 trapezoids, combine them with the one with 2 trapezoids to get even better estimate, which is here I22. But now you see that I have I12 here, this estimate, and I22. Why not combine these two to get an even better estimate, I13? And you can see 3 here, that is the 3rd level of integration, right? So the first level of integration we did basically using the trapezoid. The second level of integration is basically by combining both. And the 3rd level of integration doing another level of combining estimates. Okay, so what if I13 is not accurate enough? Well, we can even apply Romberg's integration another time. We can go ahead and get, so this is with 1 trapezoid, this is with 2, this is with 4. Well, I can go ahead and get an approximation with 8 trapezoids. Combine it with an approximation with 4 to get this I32. And then combine I32 with I22 to get I23. And then combine I23 with I13 to get I14. So now I have a 4th level of integration. It's quite involved, right? So this is one of the techniques that is one of the least intuitive when it comes to numerical methods in general, actually. Okay, so let's go ahead and actually talk about the code. So the code actually, despite the fact that the technique is a little bit involved, the code is actually quite simple. So what I did is I actually wrote it down. I'm not going to write it in this lesson because I think it's going to take a lot of time. I think because it's similar to the Simpson's 1/3 and the trapezoidal, it's not going to be a problem actually just explaining it. Okay, so the first thing I did, I defined the function I'm dealing with, and in this lesson I'm dealing with exponential. And what I did here is, and you can see from a lot of this, we're going to be calculating a lot of the trapezoid, right? So I'm going to change the trapezoid subroutine that we wrote before into a trapezoid function, right? And you can see that the trapezoid is dependent on the number of trapezoids that you're using, the upper limit and the lower limit of the function. Because when you go in, you can see h is defined in terms of the upper lower limit and the number of trapezoids, and the sum is defined also in terms of the upper limit and the step size h. And when we have the sum and when we have the h, we can go ahead and calculate the trap using h divided by 2 and the function at the upper limit plus the sum plus this function at the lower limit. So very, very simple. The only difference is that we changed it to a function, and we made a function to have the number of trapezoid as its input, the upper and lower limit. So that's the second part of the code. Now, here's the Romberg integration code. Now it looks a little bit more involved than the other two, but it's actually not. Like the code that I added extra is not that complicated of a code. Okay, so much like with the trapezoid and the Simpsons, I defined the do while for with an approximate error of 0.1. So we did this before, and also initialized the error at 100. I defined the upper and lower limit at 0 and 1. Also, in this case, in the previous lessons, I actually just wrote the exact value here. I opted, since I have the function here, might as well calculate the exact value, which is the exponential is at 1 minus exponential at 0. That will give me the exact area. Now, also in terms, we initialize n is equal to 1. Since we're using with a trapezoid, we want to start with 1. And also the difference here is I created a matrix, a 10 by 10 matrix here. And before I actually go into my loop, I created my first trapezoid, which is basically using one trapezoid here. And we said it's 1 and 1 as its indication, right? So this is the least accurate. This is the J, and this is the first level of integration. And since n is equal to 1, we're going to have 1 and 0 and 1, and this is going to call this function up here to calculate what the trapezoid is when I'm using one trapezoid. So let's actually go here. The first thing I'm going to do with the Romberg integration code is I'm going to define n. And you saw that n goes from 1 to 2 to 4 to 8 to 16. So these are just powers of 2. So I'm going to define n as n is equal to 2 to the power I. Now, given that I have I11, I need to get the integral for I21, right? So I'm going to say the integral, which is the matrix that I created here, I plus 2, I is 1, so it's going to be 2 and 1 is equal to trap, and now n is equal to 2 based on this, so 2 and the upper and lower limit. So this is going to get us what is the area using two trapezoids. So I have the area using one trapezoid, now I have the area using two trapezoids, and this is all I need to actually enact this equation here to combine them to get an even better estimate. Okay, so let's go here. This is where I define my loop for the Romberg using k. So k is equal to 2 to I plus 1. And the reason k starts at 2 because, you know, this is a second level integration. And here is what we did the first level integration. So when we're going into the Romberg, this is going to do the second, third, and fourth level integrations. Now, this is exactly the equation written out as you see here. So if you go look very closely here, let me actually close this so you can actually see the entire equation here. So yeah, this is exactly the equation that we have here. And so let's actually go ahead and see what would the first iteration be. So here n is going to be equal to 2. This is going to create the trapezoidal with 2. And this is going to be k equal to 2 to 2. So if k is equal to 2 to 2, that means it's only going to loop once, right? So it's only going to loop once because it's only going to combine this I11 with this I21 to get I12, okay? So given that I have my approximation with the Romberg, which is the I12, I'm going to go get my approximate error. Okay, so what is the most accurate thing that I have right now? Well, the most accurate thing that I have right now is the I12. So it's going to be integral 1, and I here is 1. So I12 minus, what is the second most accurate? Well, the second most accurate is the I21 that I have here, which is a minus integral 2, 1 divided by integral 1, 2. So basically, it's the new approximation minus the old approximation divided by the new approximation like we did before. And this is just for the true error, and this defines or calls the exact that we defined up here. Okay, and again, this is the integral 1, 2, which is the most accurate estimate that we have. So this is for the first loop. What about if we go to a second loop? Well, if we go to a second loop, we upped I by 1. So it's going to be 2 power 2, so now n is equal to 4. I'm going to go into this integral function. So 2 plus 1, so that's 3. So 3 and 1. So I'm creating this integral I31. And I'm using this Romberg now, and the thing that I want to go through is now it's going to be k is equal to 2 to this is 2, so 2 to 3. So you can see this is going to loop twice. So let's actually see why is it going to loop twice. Well, it's going to loop twice because it's going to combine I31 with I21 to get I22, and then it's going to combine I22 with I12 to get I13. So you can see why this is going to loop twice. Then it's going to create the approximate error true error, and you can see with the approximate error, now it's 13 because 13 is the most accurate that I have, and the second most accurate is the I22. So you're going to integral 2. Okay. And what if this is even not accurate enough? So for the first loop we got I12. For the second loop we got I13. So let's assume this is not accurate enough. So let's actually go to another third loop, which is going to generate the I14. So for a third loop, this is going to be n is equal to 2 power 3. Okay, so we're going to have n is equal to 8. Then this is going to create the 8. And then this Romberg integral, k is equal to 2 to 3, or 2 to 2, so 2 to 4, which means we're going to be looping 3 times. So let's actually see why we're going to be looping 3 times. So this got I41. So it got where n is equal to 8, right? So it's going to combine, the first loop is going to combine I41 with I31 to get I32. Then the second loop is going to combine I32 with I22 to get I23. Then the third loop is going to combine I23 with I13 to generate I14. Okay. So that's basically is what the Romberg integration is. Okay, so here this is a code that basically I wanted, so you can see this is a matrix, right? And I'm interested to see that matrix. So it's a very simple code. I said cells 27 plus I because I wanted to start here, and this is 1 plus j because I wanted to start at the second column, and I wanted to display this matrix here because I want to see all these values as I'm calculating them. And you can see that this loop is defined in terms of k, right? So I want you to see that. Why is that? So the first application, Romberg, got us the I12. The second application got us the I13, and the third application got us the I14. So if the first application, you can find that I have a 2 by 2 matrix, which is those 3, and a second application has a 3 by 3 matrix, and a fourth application has a 4 by 4 matrix. So I can define this loop based on the k, right? I can define it based on if I did 3 application, I should display to the fourth column. If I got 2 application, I should display to the 3 by 3 matrix, and so on. So let's go ahead and actually run the code. So if I run the code, I'm going to display here something equivalent to this, and I'm going to display using this code. I'm going to display the application, its corresponding approximate error, true error, and the corresponding approximation. Okay, so actually let's run the code. All right, perfect. So you can see here to get below a 0.1% error, which it actually did here, is now at 0.002%. It took 2 applications, and it had an error, integral of 1.718283, and you can see here I did 2 applications. The red indicates the first application, and that was not accurate enough because it had a 2% error. Then I went another loop and made a second application, Romberg, and I got an even accurate answer at 0.002% error. That's actually quite accurate. So let's actually try to make the code push for a third application, which means it's gonna create this, 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 and this. And since I have an approximate error of 0.002, how about we define our loop in terms of I want it to go below 0.001. So if I run this, all right, so we actually reached an approximate error of 0 and a true error of 0. So we got the exact area using 3 applications of Romberg's integration. So let me try to briefly explain what we learned here. So this Romberg integration is based entirely on the trapezoidal rule, and it states if I have one approximation of a trapezoid and a better approximation, I can even combine them both in a unique way using this equation here to get an even better approximation. And we saw that. We got, this is using one trapezoid, this is using 2, we combine them into this better approximation, and this is called a one application Romberg. And if this is not accurate enough, when I get a trapezoid using 4 trapezoids, combine them with the second to get this better approximation, then combine them with this one to get an even better approximation, which is that. If that's not even accurate enough, so if 2 applications of Romberg is not accurate enough, I can go get the trapezoid with 8, combine them with a trapezoid with 4, okay, to get this better approximation, combine it with this one to get an even better approximation, then combine it with that one to get a better approximation. And this will be the final for the third, okay? So this is 1 application, 2, 3 application, and you can see that these are the numbers that it corresponds to down here. Well, this marks the end of this lesson, and I'll see you in the next lesson.